Okay, number 6 talks about C as a function of X and T. So this, and so what is X? X is the distance from distance from injection. X is distance in millimeters. And T is time in seconds after the injection. Practical interpretations. So the partial of C, yeah, Tyler. Was there from 2 different sections? Oh, okay. Are we good on 6 from 14.1? Anyone request that? Okay. So then 14.2, number 6. Partial derivatives. Thanks for telling me, instead of making me do that whole thing. All right. Oh, is this A to the alpha, X to the alpha plus beta, that thing? So you just got to see these alpha and betas as just numbers, right? But they're just... Do I have it right here? So we want to write partial with respect to X and the partial with respect to Y. Find the partial derivatives. Okay, so we could write this. That's one way to write that. Or we could write f x, xy. So we're doing the partial derivative. So what does the partial derivative with respect to x mean? And what's that?
You take the derivative of x, ignored everything else, i.e. treat as a constant.
Everything else is constant, right? So all these, this alpha, beta, these are all constants, and then the y is constant, right? So what about a to the alpha? Stays the same. What about y to the 1 minus alpha minus beta? It's all constant, right? It's all constant. And multiplied, right? If a constant is added, what's the derivative of that? It's the derivative of a constant, just a constant with nothing else. Zero, right? The rate of change of a constant, it doesn't change, right? It's 0. But when constants are multiplied by a function, those come along for the ride, right? Okay, now we got the derivative with respect to x. So what rule are we going to use, Tyler, to do that derivative of that? Power rule. So, remember what the power rule is? So just pretend that's x to the 5th. So instead of 5, you have alpha plus beta. So do the same thing you would do if it was x to the 5th. What would you do? Yeah, what is it? Alpha plus beta. X to the? That's it. All done. Okay, what about with respect to y? So the partial of f with respect to y. We could write, so yeah, you don't have to write both of these. I'm just using both notations just so we get used to it. Both of those mean the same thing. Okay, so what about with respect to y? All of this is constant. And now we got this one. Chris, tell me.
So it's 1 minus alpha minus beta.
Uh-huh.
Then that's times y, the power of 1. Well, I guess it's just negative alpha minus beta.
Right, because it's going to be this thing minus 1. Yeah. So minus the 1, is that 1, goes away. So then you end up with negative alpha minus beta. Yeah, so we'll do another a little bit harder example. Now that you've had some of the easier examples in the homework, we'll do a little harder example, and then you'll have slightly harder ones to do for homework. Any other questions? That was 6 from 4.2. Any other homework questions before the quiz?
3.
From this one?
Yeah.
What does 3 say?
It's like the same kind of thing, but it gives you the value of f of 1, 2.
Oh, it says find it at. Oh, so they want you to, after you find the function, then they want you to evaluate it at 1, 2. That's all they're saying. Make sense?
So yeah, I was doing that. I got the x one, but I didn't get the y one.
Let's do the y one.
It's in the
So
back of the book, I know about
x squared plus 3x squared y. Minus 2y squared. And so we want to do, so tell me, Cutter, what do you think the partial with respect to y is?
It's going to be 0 plus
0.
The derivative of that is just going to be 3x squared.
Good.
And the derivative of that is going to be minus 4y.
Good. And what are we doing? 1, 2, or 2 ones?
I think it's 1, 2.
1, 2. So now that we have that function, so this gives us all the partial derivatives of y at any value, at any x and y, and so now we want it particularly at 1 and 2.
Oh, I know what I did. I kept the x squared.
Yeah, if you add,
Yeah, I kept getting that.
now that's the derivative of that is 0. It's not multiplied. If it's multiplied, you keep it. If it's added, it's
Yeah,
rate of
that's
change.
what
You can think of how does a constant change, right? It doesn't. It's 0.
that makes sense.
So then it's just what, 3 minus 8, negative 5?
Yeah,
Is that the answer in the back?
I think so. Yeah, because I added 3.
Okay, any other, yes, Sebastian?
For that number 3 one.
Yeah.
Can you do the x part of that?
Yeah, sure.
I kept getting, like 7. And it
Tell me.
was like 15 or something
Sure, let's do it. So partial with respect to x is? Tell me. Sebastian.
like that. Yes. It is x cubed. Yeah, 3x squared.
What's the derivative of x squared first?
Sorry, 2x.
2x plus
6x.
6x
Y.
y
Minus 2x squared.
minus 2y squared. Derivative of a constant. What's the derivative of minus 2y squared with respect to x? No. When you have a constant by itself, added or subtracted, what's the derivative of that? 0. When it's multiplied, that multiplies the derivative by the same amount. So that's, you save that. So the constants that you keep are the ones that are multiplied. The ones that are just by themselves, added or subtracted, derivative is 0. Was that the issue, Sebastian?
I actually think I might have.
I think it's supposed to be x cubed.
Yeah,
X to the third power, not x squared.
Yeah, it's actually.
I didn't notice that.
Anyone notice that before Cutter just did? Shame on you. Speak up, you guys. Speak up if you notice that. If no one did, that's okay. If no one did, that's okay. But
Yeah, f y.
if you notice a mistake, please speak up. All right, 3x squared.
Yeah.
All right, now we better. And then the derivative of that is 0. So it's 3x squared plus 6xy. Do you see that, Sebastian?
Oh, okay. So when it's subtracted like that, it's just 0.
Yeah, if you have a constant added or subtracted to a function, the rate of change of a constant is 0. It doesn't change. That's by definition, it's constant. So its rate of change is 0. So the derivative is 0. But when constants are multiplied by a function, that's when you keep them. But when they're just added or subtracted, those constants have a derivative of 0. Okay, other questions? David?
Number 6, what would be a complete explanation for what CO expected is?
This? partial of C with respect to T or X?
So C with respect to X.
X. Okay, anyone want to give it a try? We worked hard on this last time. So what is the quantity C? C stands for what? Concentration of the drug, right? And then X is distance in millimeters from the injection point. Okay. So anyone want to give it a try? What is the meaning of this? Do you remember we practiced this on Tuesday? We're going to practice again more today. So let's start now. Lucas, you want to try it?
I'm thinking of it right now.
Okay, you're just talking it out?
Yeah.
Okay. Did it all fall out of our brains over those 2 days?
Probably.
It's understandable. You got lots going on in your life. That's why we practice. We just keep practicing. All right, David.
So I saw there is the change in concentration of drug in response to the small change in X if T is held constant.
Okay, yep, that's true. Yep. And we want to hold T constant. Hold T constant, and then what do we let change? C, do we let X change or C change?
So by letting X change, C changes.
That's right. But
So we're changing.
X is so we're gonna tinker with the independent variable. So given a small change in distance from the injection point, and how do we symbolize that? What's a small change in distance from the injection point?
Or
Dx. Then we say, given any small change in distance from the injection point, we say the resulting what? The resulting change in concentration. Yep. And how do we denote a change in concentration?
DC.
DC is, how do we get the resulting change in concentration? Remember what we said? DC equals? What's that? This thing?
Is it Fx comma T of dx?
No. Anybody remember? So given a small change in the concentration, sorry, in the distance down the vein or whatever, the resulting concentration is calculated as? Right, and what is M?
The slope. Or,
So in this context, what is our rate of change? What is it? So what? It's this. We're interpreting this value, right? This is the rate of change. So that's our M. That's the rate of change. It's the partial of C with respect to X. So DC equals
dc dx.
partial of C with respect to X times as much as dx. And so expect that to be positive or negative. Expect that value to be positive or negative, and why?
negative.
Why negative, Kyle?
Also, distance away from the injection site would increase, the concentration of the drug would decrease.
Right. Good. Right. If so, for an increasing distance away from the injection point, we'd expect lower concentration. That means the rate of change is negative. So we're going to practice more of that. But does it kind of remember? Do you kind of remember that from Tuesday? We practiced that with the guitar string. So yeah, for a fixed time, and a little change in distance, dx, the resulting change in concentration would be the rate times the dx that you picked. Okay, other questions before the quiz? Okay, so I'm gave you 3 rates of change here. So we're going to practice outside of the multivariable situation. Easier situations that are just single variable rates of change. Okay, single variable rates of change. So each rate of change is varying continuously, but has a particular value, has a particular given value at a certain moment. So for each of these, I want you to first identify the associated independent variable and dependent variable that's associated with that rate of change, and then interpret the value of the rate of change the way we've been, with the full, broad meaning that we've been working on. So here are the 3 rates of change we're going to work on. So at a particular moment, water on the stove is heating up at 0.91 degrees Fahrenheit per second. At a particular moment, a car is getting 34 miles per gallon on the highway, and the cost of the stock is $12.50 per share. So each of those is a rate of change. So for each of those, you're going to identify what's the independent quantity or variable, what's the dependent quantity or variable. So let's just, when you have z as a function of x and y, what's independent? What's the independent?
X.
Is x independent? Anything else?
X, Y.
X and y are the 2 independent variables. Okay? Z is the dependent variable. Okay? And so a partial derivative is like partial of what with respect to what?
Of x over z to x.
Z, as an example, partial of z with respect to x. So in our units, we'll follow along, right? So the units of the rate of change will follow along that notation. That you're having a change in your dependent per change in independent. So that's to help you with this in terms of which one is independent and which one is dependent. Okay, but then we want to use our good meaning, right? Given a change in such and such, the resulting change in such and such will be, etc., such and such. Okay, so practice, take 5 minutes to practice just the first part, and then we'll go on to the multivariable functions next, okay?
The amount of time.
That's right. So now, dg, any amount of gallons, the resulting number of miles will be
That's just kind of back.
dg.
Yeah, so if you
G times G ratio.
34 times dg. Getting closer. Okay, first one, what is the independent and dependent variables? Independent is? The first one. Time, right? Independent is time, and dependent is? Temperature, right? So independent is time in seconds or number of seconds. Dependent is the degrees Fahrenheit. And what does this number 0.91 mean? What does it mean? So does it mean that every 1 second the water heats up 0.91 degrees? Does it mean that? Yes, but we want to do better than that. What can we say that's better than that? Given what?
Given a small change in time,
Any small change in time.
temperature increases 0.91
What do you want to call that? Sorry to interrupt. What do you want to call that small change in time?
dt.
dt. What can you say?
The temperature is increasing 0.91 dt.
Can I say increases? The temperature increases by how much? 0.91 times dt degrees Fahrenheit. It's a variation of degrees, so it goes up that much. Because in 2 seconds, how much will it go up? 1.8. 2 times 0.91. And in half a second, how much will it go up? About 0.45 degrees Fahrenheit, right? So what are you doing? You're multiplying whatever little time you have. You multiply it by the 0.91, and it gives you how much change in Fahrenheit there is. That's what rate of change means. Okay, how about volunteer back in the back? So number, you want to do this one, Kyle?
Sure.
Sure. First of all, what are dependent and independent?
Dependent variable is the number of miles per gallon.
Dependent on, wait, say it again. Dependent is what?
Variable is the number of miles per gallon.
Okay, so miles per gallon is the rate of change. So okay, start again.
Dependent variable would be the miles.
Dependent, okay, good.
Independent variable would be the gallon.
Right.
And then statement would be given any small change in number of gallons or DG, the amount of miles is 34 times DG.
Good. So given a DG, a small change in gallons, the change in the variation or the miles driven is?
34 times DG.
Right. 34 DG. Or say we can say DM if you want.
So then for the first one, could you do like D,
Capital T. Temperature.
D capital T, yeah.
Yep.
Okay.
D capital T equals 0.91 D little t. That's what frames the meaning of that number. That for any change in time, to get the corresponding change in temperature, you'd multiply that change in time by 0.91. All right, someone in the back. Number 3. Let's get this. Lena, Sebastian. David, you want to try? Go. Okay, dollars, dependent, good. Number of shares, okay. Okay. Okay, good. Given variation in the number of shares. And you want to call that what? DS for number of shares. The resulting what? Is it the resulting total cost? So what are we doing? We're given a variation in the number of shares. If we vary, so for instance, right now we're going to buy 98 shares. We changed our mind. Now we're going to buy 102 shares. So given the variation in the number of shares, the resulting, is it total cost of the shares? It's not a total. That's the problem.
$12.50 per share.
That's what we're trying to describe. We're trying to describe what that means. $12.50 per share. So it's the resulting variation in cost. It's not a total cost. Resulting variation in cost from that variation in number of shares. Like, for instance, we decide to buy 4 more shares. The rate of change tells us how much more we're going to have to pay, the additional cost, not the total cost. Does that make sense? Lucas?
Can I read mine?
Yeah.
Sure. All right. So, given a small change in amount of shares, the stock price increases $12.5 times the change in shares.
Okay, good. Except it's not the stock price; it's the cost. Yeah. No, it's perfect. But stock price is a different quantity. Stock price is like how much like the stock is worth. This is like we're buying shares at that price. Does that make sense? Yeah, but everything was perfect. Everything was perfect. Except you just talked about a different quantity here rather than the cost of the stock. So the resulting variation in cost is what? 12.5 times DS. And that would be like a DC or something. So what I was getting at was that the rate of change doesn't tell you like your total, it tells you the resulting variation of the dependent variable from a variation in the independent. Does that make sense? Okay, so now that we practice with these kind of single variable situations, so now the two variable situations, so now try this. So you're going to apply the same thing you did here, but they're not in context. They're just partial with respect to x at 4 comma 7 is 6. Partial with respect to y at negative 3 comma 8 is negative 0.25. So apply the same idea of rate of change to those and interpret those numbers, the 6 and the negative 0.25. Lucas got it. Lucas got it. Good job. Anybody else think they got it?
I don't know.
You almost had it.
Did you just add it to Z?
Okay, so
I don't know.
so basically, most of you got the fact that there's what's the change in x?
26.
No, the change in x. dx is 0.1. And then we know that from the rate of change, the corresponding change in z will be 0.6. So now I'm asking for an estimate of the new value of z. So f of 4.1 comma 7 is approximately equal to, so we need the old value of z, there you go, plus the change in z. So Lucas, what's the old value of z?
F of 4 comma 7.
Right, so it's going to be the old value of z, f47, plus dz, exactly. And that should make sense. This is the starting value of z. We've made a change of x of 0.1. From the rate, we got a change of z of 0.6, 6 times 0.1. So you're going to add that change in z to the starting z, f of 47. And that's your estimate for f of 4.17. Okay, so practice one more time. So how about estimate f of negative 3, 7.6. No, let's see. Sure, 7.6. So I want you to estimate f of negative 3, 7.6, or write an expression that would be an estimate for f of negative 3, 7.6. Whole process.
Okay, so I took the change in y, so I subtracted 8 and 7.6. And that change is negative 0.4.
So this implies a change of y of
So dy is negative 0.4.
negative 0.4. Okay?
So then our dz, we're going to multiply that negative 0.4 by negative 0.25. So our dz is going to be 0.1.
And this comes right out of the meaning of that rate of change, right? The meaning of the rate of change is given any change in y, it's the partial with respect to y, given any change in y, the resulting change in z is the rate times the change in y. And that is?
0.1.
Good?
So then we set it up to where it's f of negative 3, comma 7.6 is equal to,
No, keep-
set up. So negative 3, comma 8,
Uh-huh.
and then that is plus 0.1.
Which is our, what?
Our dz value.
dy, that's right, dc, exactly.
Yeah, alright.
This came from partial with respect to y times dy. Does it make sense? So we're going to be applying this later. So I wanted to give you a kind of a preview of that. But this, so and what I wanted you to see is that this is just an application of, it's applying the meaning of the partial derivative. You're applying the meaning of the partial derivative to actually now estimate a new z value, given a change in one of your independent variables. Okay, so let's Let's do this. This is not scary at all, guys.
It's just a lot of numbers.
Okay, it's a lot of numbers, but we only have to look at one at a time. Okay.
I'm good with that.
So this is a representation of a multivariable function. Okay, so this is heat index. Was that, and that might have even been one of your, was that one of the things in the homework, or was that wind chill or something? Or so this is heat index. We'll call it I. Is a function of, well, let's call it something else. F is overused, so let's call it heat index function, so H. So F, H of capital T, temperature, and humidity. What's that? Okay, so let's just start by so here is, I'll write it again here. So what do I mean by this statement? What do I mean by this statement? This is heat index is dependent on or a function of temperature outside and the humidity. All right, so tell me, this is now indicating what the temperature is 90 and the relative humidity is 45. So I want you to write an expression for the heat index and find the heat index when temperature is 90 and relative humidity is 45. So write in an expression that means the heat index and then determinants.
That's good.
Okay, so did you get the representation? Let's see. Jake, did you get the representation of that value of heat index? How could I represent it? Tell me.
So 93
Okay.
equals, yeah, 93 equals H of 90 and 45.
So the representation, he's saying little h of 90 comma 45. Agree with that? Yeah, that's the representation of the heat index when the temperature is 90 and the humidity is 45. This is called function notation. Function notation expresses a value of which variable? Independent or dependent? The function notation is this whole thing. Does it express a value of independent or dependent? Dependent, right? The whole thing as a, yeah, you see the independent variables in it, but the whole thing as a unit, this whole expression represents a value of the dependent variable, in this case, heat index. And that value is 93 from the table. Okay, so now at the same time, we want to estimate h of x 90 comma 45. Using the values in the table, can we get an estimate for the rate of change of heat index with respect to, oh, actually, I shouldn't write x, with respect to capital T. So I want the rate of change of heat index with respect to temperature. So what does that mean for humidity? We're We're going to hold it constant. So what are we going to do? We're going to be looking right along here, holding humidity constant. What's another way to express the partial of index with respect to temperature? What could I, just a general symbols to represent that? That'll help us when we to calculate this. What could I write here that's also a notation for index with respect to temperature? Good, Lena. So partial I. The reason I had you write that is because that kind of follows the calculation that we're going to do to estimate this, right? So we want what? We want a change in index for a corresponding change in temperature. So what changes in temperature do I have here? I have changes of temperature of 2. Do you see that? Okay. And on this side, what is my change in heat index for a change in 2? 4. And what about here? 3. So we'll take the average, right? We got a change of 4 on one side, a change of 3 on the other. Call it a day at 3.5. So that's 3.5 perceived degrees Fahrenheit per 2 actual change in degrees Fahrenheit, right? Or is that 1.75? And that's the rate of change, so the units are? Do these cancel out? No, don't cancel them out because we want to keep the meaning of a rate of change. And then these are actually slightly different, right? This is perceived degrees Fahrenheit. This is actual degrees Fahrenheit. So that's the units. Degrees Fahrenheit, feeling change per actual change in degrees Fahrenheit. Okay. And so now this number is a partial derivative, and we could say, what? Given any small change in what? In the temperature, the independent. Given any small change in the temperature, the what? Change in heat index
is 1.75 times
right.
the temperature.
Good. The variation in perceived temperature will be 1.75 times as much as the actual change in temperature. Right? Same thing again. All right, so I want you to estimate H sub H of 90, 445.
Yeah.
Sure. Okay. Chandler, did you get this? Tell me.
So I got it was because when you go down, you have like a change from 40.
Okay.
So for 90 going from 91 to 93.
Yeah.
And 93 to 95.
Uh-huh.
It was a change in 2.
Okay.
And you average that out with the change in 5% humidity.
Okay.
So it was 2 over 5. So for every small change in humidity,
Mhm.
it's multiplied by 2 over 5 to find the relative temperature.
The feeling temperature, yeah.
Yeah.
Yeah, uh-huh, exactly. Good job, 0.4. So so for a change, the change in humidity, the humidity that we have is 5, so that's what we have to use. And we see a change in index of 2 per change of 5 humidity, so that's 2/5 or 0.4 degrees Fahrenheit perceived per percent. Okay, does it make sense? Any questions? Okay, let's do it again. So I want you to find, so now I'm saying the temperature is, so H of 82, 90. h sub t of 82, 90. And you guys work together and agree. Agree with your partner or your table on what you're going to do.
Giorgio,
Yes.
bring it up.
All right, I'll give you one grace because you were all done there. But you have to tell me how to do this.
All right. Okay.
All right. And then not use your phone anymore. All right, okay. Can I have your attention, please? Giorgio is going to tell us about the partial with respect to t.
So for this one,
Yep.
what I did is,
Okay, can everyone have Giorgio's attention, please?
so I found how much is the change between the point before the 91 and after it.
Okay.
So, before so it's from 86 to 91, it's a change of 5. And from 91 to 98, it's a change of 7.
7, okay.
So the average is 6.
6, so average change of 6 per
Per 2.
per change of 2 in temperature.
And the degrees, the units are Fahrenheit per Fahrenheit. So
Good.
it's equal to 3. Yeah.
And so then did you do this problem?
Yes.
So now, what's the new index when the change in temperature is negative 0.2?
So what I did is I used 91, and it's 91 plus negative 0.2 times 3.
91 times,
No, 91.
sorry,
Plus
91 plus,
negative 0.2 times 3. And it's equal to 90.4.
what does that represent again? What's that represent right there?
The change.
Change in?
That's the term. The T.
Change in t? That whole thing? That's the change in t.
It's the change of H.
Oh, it's
Of
like-
lowercase h. Yeah, it's like changing I
I.
index.
Right? If the rate of change is 3, that means given any change in temperature, oh, here's a change in temperature, look. Brandon, tell me, finish it out.
Huh?
Finish it out. You seemed like you wanted to get involved, so go ahead and finish it out.
Like tell you what
Tell
the
me, yeah.
answer is? It's 90.4.
But given any change in temperature,
Yeah.
what's true?
Given any change in temperature, there is given any change in temperature, the change in the index
Yep.
is 3 times change. Given any change in temperature.
Right, the change in index is going to be 3 times the rate times the given change in temperature. Okay? What did you get for the, Caden, did you get a heat index, or I'm sorry, is it the partial of index with respect to humidity? Tell me what you did.
So I took the change of the index and held temperature constant.
Good, so we're going to go up and down this way, good, okay. So one change of 1 here and a change of 2 here, you average 2. Okay? It's really distracting, guys. Brandon, it's really distracting. It's really hard. I want it to be a loose, comfortable environment. I want you guys to be able to talk, but it just sometimes it's too much. Okay.
That 1.5 here on top. Yeah.
Oh, because that's the change in index. Okay. Good.
And then the change of humidity is 5.
And what's that going to be then?
0.3.
0.3? Okay, and then did you get the corresponding change in, or what the new index would be due to a change of humidity of 0.4?
You do 82 plus 0.4.
Take 0.4, so the rate 0.3 times. And that gives what? Change in I. And if we want the resulting, or the new index that results from that change, what would you do? So there's the change in index. Now I want to get what would the new index be? 82?
Or no, the 91.
91 plus that. So 91 plus the change gives you the new index. Just like we did 91 plus the change over here. Given any change in humidity, well, there's a change in humidity. The resulting change in index would be 0.3 times that change in humidity. So there it is. 0.12. Okay, so now how much, so now, here's what's gonna happen. So now the temperature is gonna go down 0.2 degrees Fahrenheit, and also the humidity is gonna go up 0.4%. Both changes are gonna happen. What's the new, how would you calculate the new index? If this change occurred, and also this change occurred simultaneously, how would you get the new index now? Lucas?
Wouldn't you just take the average between the two values you got?
Between which two values?
So your new i's, your approximations to the i's.
So let's pretend we didn't find the two original i's.
Okay.
Yeah. I think that would work. But let's pretend we didn't find those original two i's. And I've got this index of 91, and then temperature's going to change that much, humidity's going to change that much. What would I do to get the new index? How much does the index change according to this change in temperature? This. How much does the index change for this change in humidity? This. Are those dependent on each other, or are they independent of each other? They're independent, right? They're two totally separate things happening. They're just happening at the same time. So what can you do?
You can just add those.
Can you just add it all up? Yeah, so there's going to be some change in the index due to the change in temperature. That's this. And then separately, there's going to be a change in the index due to the change in humidity. That's this. So to get the new index, it'll just be the old index plus the sum total of all the changes due to temperature and humidity. So let's just get a number for that. And this is approximate because our rates of change are approximate. So 91, this is what? Negative 0.6 and positive 0.12. So what'd you say, Jake? It's going to be negative 90 point.
90.5.
Perceived degrees Fahrenheit. Please.
Can't you also take the two individual values and just multiply them together and then add the 91? So you take the 0.4 and then you multiply it by the negative 0.02 and then just add the 91.
But this is the rate of change. It sounded like you want to multiply this by this. That's what I heard you say.
Right, because you're changing dt, so you multiply dt by dh, and you get negative 0.08, and you add that to 91.
No, you know, these are apples and oranges, right? So temperature is its own quantity and humidity is its own quantity. So you're not going to multiply across those. You want to multiply the change in humidity by its rate of change and the change in temperature by its rate of change. Because there's the apples and oranges. They're two totally different quantities. So you wouldn't be multiplying this rate times this change, or you wouldn't be multiplying these changes together. I don't know, does that make sense?
No.
Okay, cool. David.
So I have a question about the estimate. So why do we take the estimate like before one and after?
Doing the rate?
Yes, it's a time rate. Like, why
Which rate? So
just for both, right? So basically we're finding how much change per unit.
uh-huh.
Let's take for example the period of time, right?
Okay. So you did 3 over 10?
Well, I was just wondering like why we would take that.
Because it gets the, why we would what?
Why we would estimate like temperatures versus temperatures. Right next to this, like the temperature, the actual temperature changed 2 degrees, increased 2 degrees, or decreased 2 degrees. So why we take estimates from those two? Why would we just take it from one?
Because the rate of change can be different here than it is here. Like, so the rate of change is itself a function. It changes. It's like the rate of change is a phenomenon that's just right in the local area of values of the independent variables. So there's a rate of change associated with 82 and 90, say a rate of change with respect to temperature. And then there's could be a totally different rate of change associated with 80 and 55. So as soon as you start changing one of these variables, the rate of change can change too. So you can only look in the local area to calculate it. Does that answer it? Yeah. So yeah, these rates of change can change themselves. So as soon as you go somewhere else on the table, you may have a different rate. We don't want to use that information to help us find that rate. Does that answer it? Yeah. Other questions? Okay. Okay, so notice what we're doing now. So this is the first time now, instead of isolating the variables and taking a change of one variable versus a change in the other. So now it's like we're taking 2 changes in combination. So what did I do? I took a change of temperature. So what was you kind of think of it in proportion. The change I took in temperature, or the change I took in humidity was like -2 times as much as the change I took in temperature, right? So that would kind of be like if I was at this point right here. If I went -1 in this direction, at a ratio of 1 to -2. So 1 to -2. That's -1 to -2. -1, so -1 to +2. Right? Isn't that like -1 to +2, that ratio? So it's kind of like instead of going just right or just up and down, it's kind of like we're going, like when I had you do this problem, it was kind of like we were going along this trajectory in the table and asking for the resulting change in index along this trajectory in the table where changes in humidity were -2 times as much as changes in temperature. Does that kind of make sense? Yeah.
So are you saying like we're making like a linear function, tangential function to the grand scheme of I function?
Right, so it's like, let's do a graphical version. Okay, so that's just an intro to that. All right, any questions on this? Any other questions on getting these rates of change or these changes or the new estimated index? All right, let's look at a new example here. So here's another multivariable function. This is given as a contour plot.
Okay.
Where's my pen? I just had it. There it is. All right. So this is the wind speed in a tornado? A function of the volume of the tornado and distance from the center. So we'll just call it F. So volume and distance. So I write these here.
Can you label the coordinate system? Like, what is the,
What's that?
so the, like.
So this is the volume of the tornado in millions of cubic feet. So this is the volume
Okay, so
quantity.
it's
And then this is the distance from the center in hundreds of feet.
the- Okay.
Okay, and then the contour lines give us the values of the dependent variable, which is the wind speed in miles per hour. Okay, so look at, I want you to estimate f of 4, 2.5. And then see if you can do this based on what we just did with the table. Now it's a graph version of the same thing. So f sub v of 4, 2.5. And fd of 4, 2.5. So what is this asking for? It's asking for the wind speed of the tornado. What? That's 4 million cubic feet at a distance of 2,500 feet from the center, and then the partial derivatives. So use what you learned from the table. Use the same kind of process from the table, but now you have to get those values from this contour graph, this contour map of the function. See if you can do it. See if you can do it. Wind speed is about 100 miles per hour. Maybe a little bit. Well, 75 is up here, right? 75 is this red line. So maybe just like, you could say 95 or something, so just under 100. But 100 means you get it. If you said 100, it means you get it. Okay, what about partial with respect to v? So what do we need? So we could say that that's del what? Del what?
dw over d.
Good. All right. So that's exact. And then, so that helps us to form the estimate for the rate of change. So we need a change in v. So an easy one that I see is kind of like right here. You see that? That's an easy change in v and corresponding change in wind speed. So what's the change in v? 1. And the change in wind speed is 25. Does everyone see that? So you're picking off numbers now. So that equals 25 what? Miles per hour per millions of cubic feet. Yes, please. What's that? Because all these are, it's giving the z values for every other line, the black lines. You see there's black and red lines? So it's giving you the z value for every black line, which are 50. So then the red lines would be then in between that would be 25. So to get from one line to the next is a change in wind speed of 25 miles per hour. Do you see it?
Yeah.
So this is 50, 100, so this is be 125, 75. Okay, what about the partial with respect to distance? So that'd be so now we might want to go up and down like we did in the table. We did both sides. So we kind of have to estimate. So either you go 25 and you estimate the distance, or you go a distance of 1/2 and you estimate the wind speed. Does that make sense? You got to kind of pick one or the other. So let's go 25 in d wind speed. That's 25. And so what would you estimate as the change in distance for that? 0.3, right? Because this is 0.5 from there to there, so 0.3. But then on this side, it's much different, right? So we might want to do an average in this case. So let's, well, maybe not that much different. What is, so we'll do it this way. Also 0.3? Yeah, pretty close. So 25 up, that's a change in D of 0.3. And then a change of wind speed of 25 is also a change, so that's pretty good. But what's happening to the wind speed for an increase in D? Do you see what's happening? This is increase, this is delta D of 25. Wind speed is decreasing, right? So we need negative 25 per.
0.3.
Anyone got a number for that? What's that? Negative 83.3. And what's that going to be? Miles per hour per? 100 feet. Okay, so estimate the new wind speed. When I don't know what it is. Let's see. I want dV to be negative 0.4, sorry. That's what I want. So two changes occur. The wind speed, the volume of the tornado goes down by negative 0.4 million cubic feet, and the distance from the center goes up 0.1 feet. Excuse me, 0.100 feet. Estimate what the new value of the wind speed is.
So wait, now, so the distance went down?
No, the volume went down, negative 0.4. The
Okay.
distance went up, 0.1. So Philip, can you tell me what to do? Okay, great.
So, so we added up the dV and the dt, right? The negative 0.4 and the 0.1.
You want to add those together?
I think that's maybe what we want to do.
David, do you want to take over? Okay, so just keep the noise down so I can hear David. So you want to do what? Right. What does this mean? This partial derivative means given any change in volume, the resulting change in wind speed is 25 times the change in volume. Given any change in distance, the change in wind speed will be the rate of change times the change in distance. And then starting wind speed plus the change in wind speed due to the volume change plus the change in wind speed due to the distance change. Does someone get a final answer? 81.67 is a new estimate for the wind speed. Okay, have a good weekend.